Last lecture, we went through the basics of mass spectrometry. Today, I'm going to navigate you with the first step of mass analysis, sample preparation and derivatization. In this lecture, you will learn the principle of a variety of sample preparation techniques, including protein precipitation, solid phase extraction, solid phase microextraction, liquid-liquid extraction, supported liquid extraction, and derivatization steps in GC analysis. Lastly, we will go through some commonly used sample preparation protocols for different kinds of mass analysis. Let's begin with protein precipitation. For small molecule mass analysis, proteins and lipids are the common sources of interferences. Therefore, the main purpose of protein precipitation is to separate the protein from the solution, reducing the potential interferences of mass analysis. The efficacy of protein precipitation method varies depending on the solubility and molecular structure of the protein. Regardless, hydration shell is the target of all protein precipitation methods, as the hydration shell contributes to protein solubility in aqueous solutions. The protein precipitation techniques can be divided into three categories: acid precipitation, salting precipitation, and alcohol precipitation. In the following slides, we will introduce each technique in detail. The first one is acid precipitation. As every protein has a defined isoelectronic point, little changes in a medium pH value can have an impact on the protein structure. Under low pH conditions, the proteins will be positively charged, causing the disruption of hydration shell. The protein will usually lose its biological function after acid precipitation. Trichloroacetic acid is the most popular acid used with this method because it is highly reactive and can be used in small amounts. The second one is salting precipitation or salting out. Salt ions will compete for the hydration shell to stay in the solution, causing the restriction of the available water molecule for the proteins. The hydrogen bonds between proteins and water molecules are therefore destructed. The interactions among proteins still exist, causing the protein aggregation and precipitation. Zinc sulfate and ammonium sulfate are the typical salts used for the salting precipitation. For mass analysis, we prefer to use volatile salts to avoid clogging the ion transfer tube. Salting precipitation can keep the protein intact, so it is widely used in biological experiments. The last one is organic solvent precipitation. Alcohols can displace the hydration shell and surround proteins, which leads to aggregation and precipitation. It is possible to preserve the biological functions of proteins using this method. However, it requires a well-controlled experimental condition. The most predominantly used solvents were ethanol, methanol, acetone, and acetonitrile. Different solvents to sample ratios can affect the protein precipitation efficiency. Overall, the more organic solvent you use, the greater efficiency you can get. However, the improved efficiency has a marginal effect, where 2:1 organic solvent to plasma sample ratio shows a satisfying protein precipitation efficiency. Solid phase extraction is the other commonly used sample preparation technique for mass analysis. The solid phase solvent can retain the interfering substances or the analytes by incorporating the washing and elution steps. The analytes can be separated from the interfering compounds. Additionally, the SPE procedure can concentrate analytes of interest in the sample. The solid phase extraction has 4 major steps. The first step is conditioning, which can further be divided into 2 sub-steps: activation and initial condition. The non-polar adsorbents are usually activated with 2 to 3 column volumes of an organic solvent, such as methanol, and then followed by the solvent in which the analyte is dissolved, usually the pure matrix or water. The polar solvents are conditioned with non-polar solvents. You should keep the adsorbent bed filled with the solvent before sample loading. The second step is sample loading. Sample loading can be achieved using a positive or negative pressure. You should evaluate if the SPE packing material's capacity is enough to retain your analyte. Sample loading can be followed by washing step or elution step, depending on whether the adsorbent can retain the analyte or not. If the adsorbent can retain the analyte, then we would proceed to step 3, washing. Ideally, the washing step can get rid of the interference but keep the analyte of interest in the adsorbent. If the adsorbent can not retain the analyte, then the washing step can be omitted. The final step is elution. In this step, the analyte shall be eluted using a suitable solvent. The elution speed depends on the column or cartridge dimensions and the quantity of adsorbent. The SPE extraction mechanisms can be categorized into 3 major mechanisms: reverse phase, normal phase, and ion exchange. The reverse phase mechanism is suitable to extract hydrophobic or polar organic analytes from aqueous matrix. The normal phase mechanism is designed to extract polar analytes from non-polar organic solvents. The ion exchange mechanism is used to extract charged analytes from aqueous or non-polar organic samples. Depending on the functional groups, the ion exchange mechanisms can be further divided into 2 groups: cation exchanger or anion exchanger. This table summarizes the typical extraction protocols for reverse phase, normal phase, and ion exchange SPE, just for your reference. The other variants of SPE is online solid phase extraction. This setup uses 2 chromatography columns. One is the SPE column, the other one is analytical column. Configured with 6 portal valves, this system can achieve online solid phase extraction, which can save the time and the cost of the traditional offline SPE. However, the offline SPE system may still have a superior sensitivity compared with the online SPE system. Microdialysis is an in vivo sampling technique that can easily coupled with LC mass for kinetic analysis. The front end of the microdialysis probe is a semi-permeable membrane with a certain molecule weight cutoff size. If the analyte is smaller than the cutoff size, then it can diffuse across the membrane, get into the dialysate, and get analyzed. If the analyte is larger than the cutoff size, then it will be excluded from the analysis. Microdialysis coupled with online SPE is a very useful for the pharmacokinetics or toxicokinetic studies in animals. This is our previous work using microdialysis coupled with online SPE for the toxicokinetic studies of aquaamine glutathione conjugates in SD rats. Using this setup, we can automatically collect the concentration data every 15 minutes for 8 hours, which will reflect a more accurate and relevant kinetics data, especially for the unstable metabolite. A recent progress is high-throughput SPE, rapid-fire by Agilent Technologies. This system incorporates a tiny SPE cartridge with a variety of different choices of adsorbents into an automatic programmed SPE protocol. A single SPE run can be completed within only 1 minute. Solid phase microextraction. SPME is a filament coated with a certain adsorbent, which can retain the analyte of interest. SPME can be further divided into two classes: direct immersion SPME and head-space SPME. Direct immersion SPME is similar with SPE, working with the solid-liquid interface. On the other hand, head-space SPME works with a solid-gas interface. Either ways, the principle behind SPME is the same, using the partition between medium, like gas or liquid, and the filament, which is solid. SPME combines analyte sampling, isolation, and enrichment into one simple step. By controlling the polarity and thickness of the fiber coating, maintaining consistent sampling time, and controlling several other extraction parameters, SPME allows an analyst to ensure highly consistent and quantifiable results from samples, even when analyzed are at low concentrations. The advantage of using SPME include solvent-free, easy to automate, non-destructive to samples, extensive applicability, fibers are reusable, and compatible with GC or HPLC instrumentations. Liquid-liquid extraction is the other commonly used sample preparation technique. Liquid-liquid extraction typically uses two solvents that are immiscible or only partially miscible. One is aqueous phase and the other one is organic phase. Depending on the compound's property, it would prefer to stay in one of the solvents. By taking the compound enriched layer, we can achieve the goal of sample preparation. Based on the analyte and the solvents used, LLE can be performed with three scenarios. The first one is the extraction of neutral compounds. In this case, our analyte prefers to stay in organic solvent. We can extract the neutral compound by applying an organic solvent several times. The second scenario is the extraction of acidic compounds. In this case, we can use aqueous base to extract the acidic compounds. Under basic pH, acidic compounds will be deprotonated, existing as an ionic state, which is soluble in water. By collecting the aqueous phase, we can extract the acidic compounds. The third scenario is the extraction of basic compounds. In this case, we can use aqueous acid to extract the basic compound. Under low pH, basic compounds will be protonated, existing as a positively charged ionic state, which is also soluble in water. By collecting this aqueous phase, we can extract the basic compounds accordingly. Supported liquid extraction is a modified form of liquid-liquid extraction. In SLE, the first step is to load the sample solution onto the diatomaceous earth. Next, a water-immiscible solvent is then passed through the SLE bed, extracting the target analytes from the samples for further analysis. The SLE method significantly increases the interaction surface compared with LLE, which improves the analyte partition from aqueous to organic phase. In the following slides, we will talk about the sample derivatization in gas chromatography. There are several purposes of applying sample derivatization in gas chromatography. The first one is to enhance the compound's volatility, as GC is more compatible with volatile analytes. Usually, the derivatization step will replace the active hydrogens with a functional group such as OH, COOH, SH, and NH, etc., which in turn will increase the compound's volatility. The second purpose is to enhance the separation. This figure illustrates the role of derivatization in improving the chromatography separation. The triangle and diamond cannot be separated under the original condition. After the derivatization, we can successfully distinguish the peaks of triangle or diamond derivatives. In addition, the derivatization step can generate more significant differences between the analytes and the matrix, which will reduce the potential matrix effects. Sometimes, the polar analytes may interact with the stationary phase aside from the intended interactions. This kind of interactions is secondary interaction. The secondary interactions only occur with a portion of the molecules, which can generate peak tailing. Sample derivatization can form protection groups, which can minimize the secondary interactions and those improving the peak shape and separation. In addition, the derivatization can also improve the compound stability. For instance, the derivatizations on the active hydrogen of thiols can avoid the formation of CO3 group, and those increase the stability of the compound. Sample derivatization can also facilitate the chiral separation and improve the sensitivity as it can increase the compound's volatility, which is preferred by the instrument. Here, I will introduce a typical sample preparation protocol for small molecule analysis using LC mass. In this case, we aim to analyze the levels of tetrachloroethylenes metabolized in liver, kidney, serum, and urine. For the analysis in liver and kidney, the tissue samples were subject to a homogenization step, spiked with internal standards, and then extracted using liquid-liquid extraction and solid phase extraction. For the serum analysis, we performed protein precipitation to get rid of the albumin in the serum, and then use SPE to selectively collect the tetrachloroethylenes metabolites. For the urine analysis, we applied protein precipitation and dilute the sample with ammonium formate buffer prior to mass analysis, as mass spectrometer is not compatible with non-volatile salts. This is the SPE protocol to extract the tetrachloroethylenes metabolites. For the condition step, we applied acidified methanol for the cartridge activation and deionized water for the initial condition. Next, we load the sample onto the Strata XAW cartridge and then wash with 300 microliter of deionized water. Finally, we eluted our analyze using basic methanol. The eluent is collected, dried under vacuum, and then reconstituted with the mobile phases of initial chromatography condition. Using the initial ratio to reconstitute the sample can avoid the retention time shift. Methanol and chloroform system is the most commonly used method to extract lipids for mass analysis. Originally, methanol and chloroform mixture is a monophasic system. After homogenization with tissues and cells, there will be 3 layers. Methanol layers containing the salts, carbohydrates, and some proteins. The chloroform layer containing lipids, and the middle layer containing the cellular debris. However, the lipid located in the bottom layer, it is difficult to collect compared with the supernatant. Therefore, MTBE methanol water system is then introduced for the lipid extraction. MTBE has a smaller density and a lower polarity index compared with methanol. Lipid prefer to stay in the solvent with low polarity index. Therefore, lipids will stay in MTBE and the supernatant in this system. This protocol would make it easier to collect the lipid extract. Despite that, we introduced many extraction methods. The future perspectives are to minimize or get rid of the sample cleanup procedure for the exposome or non-targeted analysis. If you are interested in this topic, I highly recommend you to read this review article in Science. Alright, that's for today. Bye.